Hey everybody, it's Adam again, and we're going to continue on talking about epidemiology and biostats. And today we're going to talk about a few challenges that we'll run across when we are discussing statistics in the medical literature. So today we're going to talk a little bit more about multiple comparisons. I've kind of alluded to it previously, but we'll talk about it in more detail here. We'll determine when we should use a correction to help account for using multiple comparisons. We'll delineate the multiple comparisons trap that you can run into, and then we'll look at things like the Gaussian distribution as an ideal model, and then we can talk about the concept of normality testing to apply that to data, so that way we can determine what kind of distribution type we're dealing with. We'll talk about outliers and understand their impact on a data set, and then we'll understand the concept of robust statistics. So first off, we're going to talk about multiple comparisons. So the problem we have here is that if I were to make two independent comparisons, the question is, what is the chance that one or both will result in a statistically significant conclusion? Or just by chance, right? And we talked about that the first will not be significant, 0.95 times, right? Or 95% of the time it should not be. Because we talked about that, that level of significance for us being that, if you found one of those results that was in that 5% of the outliers there, that you would consider that to be, very low probabilities just due to chance alone. And so you consider that to be statistically significant. On the other hand, then once you have a second comparison, which also has a 95% chance to be considered not significant, we'll start to add up those chances together. And so when you do that, you'll find that you have around a 10% chance now of finding a statistically significant result. Okay. So we can generalize that with more comparisons, where essentially we can look at this k constant, which is the number of independent variables that we have, and the chance that all of them will not be significant is basically 0.95 times k. And so the chance that one or more of those comparisons will be statistically significant is basically 1 minus that 0.95 times k. I'm not going to have you calculate this on a test by any means, but the point being is that if you make lots of comparisons, you are likely to find some statistically significant results just by chance alone. We talked about that before when we're comparing all these different, hospital admission types based on people's astrological sign and how that led to many statistical associations being found there, even though we know that there is very unlikely to be a true link between astrological sign and hospital admission. Not saying there absolutely isn't one, because again, with statistics, we can't be absolute about anything, but chances are likely it's not too great. And so you can kind of graphically visualize this when we're looking at basically, you can see here the number of comparisons that we have. So we were to say, for instance, if you're kind of to go through a large data set and you start to look like, well, what's the association between age and hospital admission? And then now let's look at income in hospital admission. Now let's look at education in hospital admission. As you keep increasing the number of comparisons that you have, you're going to see that by the time you're going to have this nice kind of increase in the number of, or at least the percentage likelihood that you're going to find a significant association there, right? Or something that will be statistically significantly different. And so we know those to be type 1 errors, right? Those are things that we say are statistically significant, and we reject the null hypothesis when it's not actually true. And so we need to make sure that we are taking into account these multiple comparisons, and so we have a few methods to get around that. And so we have this term called a family-wise error rate, which is basically when each comparison is made individually without any kind of correction for multiple comparisons, you would see that the traditional 5% significance level, or that 0.05, is going to apply to each in a per comparison error rate. And so we mentioned that the chance of random sampling would lead to this particular comparison to an incorrect conclusion, and that the difference is statistically significant without this particular null hypothesis is true. So again, that's going to be larger chances for type 1 errors. So when you do that per comparison error rate of looking at a 5% significance level, again, that's what we saw in that graph, where you do the more comparisons without making any corrections, you're more and more likely to make a type 1 error. So with multiple comparisons, what we can see is that if you were to redefine what your significance level is based on the chance of one or more of these statistically significant conclusions, if all of the null hypotheses are actually true, what we can actually see is that, if you were to set the usual alpha level of 5% or 0.05, and all of the null hypotheses are true, then the goal is to basically have a 95% chance of obtaining zero statistically significant results with these comparisons, right? So again, this 5% chance is going to apply to the entire family of comparisons, really. So if you were to make, say if you were to look at one comparison, you could say, okay, well, there should be a 5% chance it'll be statistically significant. Now, if you were to have two, you can start to divide that in half. So you can basically say, well, I want to make sure that I only have a 2.5% chance to find statistically significant results for these two individual comparisons. That way, in total, it equals 5% again. Because you should really find 95% of these comparisons are going to be basically not statistically significant, assuming the null hypothesis is true. One way we can do this is called the Bonferroni correction. It is not the San Francisco treat, unfortunately, but it is a very good way to help us getting around the multiple comparisons problem. This is the simplest way to achieve a family-wise error rate. And basically, you divide the value of alpha by the number of comparisons you're going to make. So I mentioned in the last slide, if we had two comparisons, you take 0.05 and divide it by 2, so you'd have 0.025. And basically, then you would define all of your comparisons as statistically significant only when the p-value is less than that ratio. So for instance, if I was going to make an experiment where I made 20 comparisons, the previous graph would show that if I used a alpha level of 0.05 for each of those, I would have roughly a 65% chance of obtaining one or more statistically significant results in that case. And so if the Bonferroni correction is going to be used, a result would basically be declared statistically significant only when the p-value would be less than 0.05 divided by 20, or in this case, 0.0025. So by doing this, you make things more stringent, you make it more difficult to make a type 1 error, but on the flip side of that, you're going to increase your risk of a type 2 error. And as you remember that, type 2 errors are when we do not reject the null hypothesis when it actually is false, right? It's a false negative that we're making there. And that rate is going to go up because we've made it now more difficult to find significance, because again, you'd rather make a type 2 error in general than a type 1 error. So some of the traps you can run into with multiple comparisons. So this is what we call data torture, and this is something that was illustrated back in 1993, where basically investigators, if you don't have a clear plan ahead of time, they can analyze the data in many ways. So for instance, say you have the statistician that says, okay, so you already have calculated all the p-values, and the surgeon says, yeah, I used a multinomial logistic regression, which is something we'll talk about a little bit later on. But the statistician goes, okay, well, how'd you come up with that? And so the surgeon says, well, I went ahead and tried each analysis on this software called SPSS on the drop-down menus, and I went ahead and found whichever one gave me the smallest p-value. Not super scientific, right? So again, this is not something where you just want to keep making comparisons until you find something that sticks. This is something where you really need to have a plan going into, or the researchers need to express what their plan was going into it, right? A lot of times when you're evaluating the literature, you kind of have to take the author at their face value and trust in what the peer review process was to make sure that the stuff they're getting published is up to snuff. Right. Another good example of this is Mayor Marion Barry. Basically, he was mayor of Washington, D.C. It's a very violent town. And he said that outside of the killings, Washington has one of the lowest crime rates in the country. Right. If you actually look at it, if you took out all the murders that happened there, Washington actually has a very low crime rate. But again, you're kind of cherry picking at that point, trying to make the data look good. And so we can't really do that. We need to be a little bit more scientific when we're evaluating these things. So there are many ways to wring statistical significance out of data, right? So we can do things like changing the definition of the outcome, right? We can say, well, we didn't really find really good results when we use this outcome, say, of blood pressure lowering by 10%. Let's go ahead and change it to 5%. Maybe we'll find something there. Trying different criteria for inclusion and exclusion. So that way you would either include different types of patients or maybe exclude different ones that maybe have been skewing your data. Doing things like arbitrarily removing outliers. This is really a big no-no. You need to include all the data there, even so you can at least address it to say, hey, this is an outlier. This is why we think they're outliers. You still need to analyze your data with those people there, because they could be a sign of actually something else going on that you didn't really anticipate. Some people will do things like clumping or separating groups differently. If anyone has ever heard the term gerrymandering, this is a very kind of hot topic in the political world, where basically people who have control of how things like congressional districts are being set up, they will do things like lumping certain groups of people together in order to make it so that a certain political affiliation is going to be favored when the voting time comes, right? And so there's some very good videos I'd recommend looking up on YouTube where you can find out more about gerrymandering. It's actually kind of interesting, where the actual the beginning of that name actually came from. And so then again, trying different statistical tests until you find the one that really sticks. So again, eventually you're going to find statistically significant findings just from chance alone, especially from any kind of reasonably complicated data set. Okay, and so looking at the number of possible comparisons is not determined in advance and is going to be almost unlimited. You can skew the data any way you want. You can slice it, dice it, do all sorts of things, and find something of significance. Now, is that actually good science? Absolutely not. And so this is why researchers need to have a plan before going into these situations. So looking at publication bias, this is actually a really interesting thing here where editors, as I've mentioned before, prefer to publish papers that report results that are statistically significant. No one likes to publish a paper saying, hey, I had this really good idea, I tested it out, and guess what, it doesn't work. It's not super interesting, and that's not going to get necessarily more people buying those journals and things like that. And again, the chance of observing a significant result in a published study can be much greater than 5%, depending on how these studies are being done. So back in 2008, there's a paper done by Turner where they were looking at these industry-sponsored investigations of the efficacy of antidepressant drugs. And so between 87 and 2004, the FDA reviewed 74 such studies and categorized them as either positive, negative, or questionable in their validity. They found that 38 studies were positive, and 37 of those actually ended up getting published. On the other hand, though, 36 ended up being negative or questionable, and guess how many of those were published? 22 were definitely not. 11 were published with a spin on them to try to show a little bit more kind of positive results, and 3 of the negative studies were published with clear negative findings. So only 3 out of those 36 that said, these antidepressants maybe they don't work great for the indication we're looking for. Those did not get, or those are the only ones that got published. So again, people like to publish positive things. Science is based on being able to replicate findings, and a lot of times people don't want to publish articles of things that have already been shown in another study. I will say that this is a pretty good video. If you guys like John Oliver, I will say, warning, there's some adult language here, but if you'd like to watch that, I think it's pretty good. Kind of showing you a little bit how kind of the mainstream media will try to find and look at some of these studies that are out there, and how that information really gets transmitted down to your patient. So it's really, really important that when a patient comes up and say, hey, I found this really good study, I want to try this for my hypertension, or I want to try this for my diabetes, you can have a good scientific talk with them and kind of tell them why yes, this might be a good idea, or no, it's not a very good idea. And so again, I recommend watching that if you are interested. So I mentioned when you were doing, when you're trying to properly interpret a p-value, it's really important that the experimental protocol has to be set in advance. It's called a priori setting of these different parameters. So what patient population you're going to be looking at, the sample size that you're going to use. And again, a lot of that comes back to power analyses, as I mentioned previously, type of data collection you're going to do, and the results analysis. It's really tempting to try to run the experiment more times in sequence to try to reach a statistical significance, right? This is a very informal approach and should not be used. It would not be considered valid. Now, again, when you're reading an article that came published out in JAMA, is there any way to tell if they actually did that or not? Well, you're kind of going off the good faith of the publishers and off the researchers. But again, we don't really know, and we may never know. So again, if the experiment is going to continue, if the result's not significant, and only stops when it reaches significance, again, not very good science we're doing there. So another thing we can do is to look at multiple subgroups. So sometimes if you were to look at a large sample set of patients and you didn't really find anything of note or anything that's statistically significant, what you can sometimes do is break down those patients into multiple subgroups, right? This way they're going to get more granular on the type of patient you're looking at. And so for instance, if we were looking at this kind of heart disease mock study, and so we had 2 randomized groups that were given the same treatment, and we went ahead and identified 6 subgroups based on things like either gender or ethnicity or on lots of different things. And what we found was that the sickest subjects in treatment room B had a statistically significant improvement in their survival. This p-value did come at less than 0.025. Now looking at this, the chance of obtaining a statistically significant finding with the number of comparisons here, if you did not do a correction like the Bonferroni correction, would be 26%. Even if all the null hypotheses were true in this case. So again, way too likely to find something that isn't truly there. And so if all the subgroup comparisons are defined in advance, then it's possible to correct for this. You can do things like that family-wise error rate where you would take the 0.05 divided by 6 and then be able to look at a little bit more in detail of those things. But unless you do that, you're not going to really be able to get truly valid results. Some other things to consider, things like disease clusters. So let's say, for instance, you had 5 children in a particular school who all developed leukemia last year. So the question is something like that a coincidence? Is it related to some sort of exposure that they all shared? So really the research question comes in and says, what is the probability that 5 children in this particular school would all get leukemia this particular year? And you can calculate that based on leukemia rates published in children. You could find, say, what are the likelihood that this could actually happen? So, but what really the question should be is what is the probability that 5 children in any school would develop the same severe disease in the same year? And so now the question is going to require defining the population of the schools, the time span that you're looking at, and severity of the diseases. In this case, you may see that there's like 1,000 clusters that get reported each year. Now, 3/4 of them are not really clusters and are not further investigated, but then the other quarter are generally going to be found to be coincidence after investigation. So again, chance alone can certainly cause a cluster. Does not always mean that they're, and again, our minds are hardwired to look for patterns. So if you saw 5 kids that all develop leukemia, you would think, hey, there's probably something here, even though if you actually did the investigation, you see that coincidences can be extremely common. Okay, so the next thing we're going to be looking at is whether or not a distribution can be considered to be Gaussian or not. And again, we talked about Gaussian distributions being the same thing as normal distributions. So again, the Gaussian distribution is not, it really is an unreachable ideal. And again, we can see that in order to determine if the data set that we're looking at, the sample that we're looking at, is Gaussian or not, we have some tests that we can do that. Okay, so again, a lot of times when you're looking at the medical research, you're going to see that a lot of people go under the assumption that the data that they're looking at, the samples they're looking at, are coming from a normal distribution. Okay, and so you'll see that with the ideal Gaussian distribution, this is going to include very extreme numbers in those values, right? They're going to have some very low negative numbers, some super high positive numbers. And what we tend to see is that in science, values are going to have kind of a biologic, physical, and physiologic limitations that really don't allow for extremes. So for instance, when we were looking at that temperature data, you're not going to find people who have a temperature of, say, 28 degrees centigrade, because that would be very, very cold. Similarly, you're not going to find someone who has a temperature, let's say, 78 degrees centigrade, because they would be dead. So the thing here is that, why use these tests that rely on this Gaussian distribution? Okay, mainly the tests are going to be useful when the data is sampled from a distribution that approximate this, and so a lot of the tests that we have are based off the assumption that you're working with Gaussian distributed or normally distributed data. So looking next, we'll see that the next figure shows some simulated data, and we're going to see that each of these distributions shows a distribution of values randomly chosen from a Gaussian distribution. So unless you're going to find that the samples are really huge, you're going to find the distribution tends to look less symmetrical. So we mentioned that when you're dealing with a typical Gaussian distribution, that it's going to achieve that kind of bell-shaped curve. And so when you're looking at the number of people that they're looking at for these sort of things, and this kind of goes back to that body temperature example, say you were only looking at, say, 5 data points, okay? So this could come from a normal distribution, but again, just due to random variation, you may not find that kind of typical, Gaussian kind of curve, that bell-shaped curve we know and love. But if you were to increase the number of people you're looking at, you're going to start to get more of these extremes in values, right? You're going to start to get things, and again, this is kind of frequency counts of the number of people who hit these different temperatures. So you can start to see that as you get more and more people, so this N of 12, that you're going to be able to find something that looks a little bit more like a Gaussian distribution, right? And then if you're looking at the N of 130, you see here, as you increase that sample size, it gets larger and larger, you're more and more likely to end up seeing those curves that tend to look much more like a bell curve, right? So again, this is something that you may be looking at a small set of data and may think, hey, this doesn't really seem like it's normally distributed, but it could really and truly be. And so this is why it's important to realize that our eyes are not good at picking up on these sort of things, and we need to use these what we call normality tests, or tests for normalcy, to determine if the data is truly normally distributed or not. So again, these tests for normality are going to be statistical tests that we can use to see how much, or to quantify how much a data set is going to deviate from those expectations of a normal distribution. Again, I've probably failed every normality test I've ever taken, which you guys probably know already, but these are going to be applying back to your samples you're looking at, or the researchers are working with. And so the first thing we need to do is to quantify how far a set of values ends up differing from the predictions of a Gaussian distribution. And there's going to be lots of different tests to do this, and with lots of complex names. We're not going to worry about them so much here, but in case you do see them, if you see a test for normality or a normalcy test, like those are the kind of things that they're doing. They want to check to see if their distribution is truly Gaussian or not, and if it is, then you can utilize certain types of statistical tests, and otherwise you have to use a different set of tests. So basically, when you perform one of these normality tests, you're going to find that it spits out a p-value for you. It's going to try to answer the following question: that if you randomly sample from a Gaussian population, what is the probability of obtaining a sample that deviates from that Gaussian distribution as much or more so than the sample does? So basically, this is kind of looking at the same kind of thing that a normal p-value would tell you. You know, how much does, say, the sample differ from a population, or these two groups differ from one another? But this is trying to say how much does your sample deviate from the Gaussian ideal? And so if you have a very small p-value, again, usually less than 0.05, you're going to be able to see that this is probably going to be significantly different from a true Gaussian distribution. Right? So high p-values are going to mean that you can retain your null hypothesis, and that means that the null hypothesis is that the data is sampled from a Gaussian population. So again, if the p-value is large, the data is not inconsistent, or it is consistent, in this case with double negatives, with a Gaussian distribution. That means you cannot reject the null hypothesis, and then you assume that your data is coming from a Gaussian distribution. Okay? Normality tests can demonstrate that deviation that you see from the Gaussian ideal, it can be expected to happen just by chance alone. Okay, and so what you're going to find is that the higher the sample size you have, the more power you're going to have to be able to find if there's any true differences there or not. I mentioned already that if you have a small p-value, this typically means that you can reject that null hypothesis, and that the data that you're looking at is skewing enough away from that Gaussian distribution that you are unable to say that, yes, you know, this is just due to chance alone. This data is skewing far enough that we can say this is probably not coming from a normally distributed data set. So what to do when you fail and the data that you're looking at fails a normality test? Basically what you can say is that, okay, well, maybe the data is coming from some sort of other identifiable distribution. So there's other types out there like log normal, which we not going to cover in the scope of this class. But there's possible there's other types of distributions out there. You may have a few outliers that may be causing a normality test to fail. So you can do things like running an outlier test. There are different tests you can do to see if the values that you have there are truly outliers or not. And in some cases, the deviation is pretty small. You may not need to do anything. On the other hand, though, what you can do is switch over to what we call non-parametric test. Basically, what you see is if you're using a parametric test, these are going under the assumption that you have a normally distributed set of data, right? It's coming from a Gaussian distribution. Otherwise, we're going to use non-parametric tests. These don't assume that you have a Gaussian distribution, and so what you're going to find is actually it's more difficult to achieve significance with non-parametric tests, but because of that, you're less likely to make type 1 errors, and you're also, we're going to call those to be more robust, meaning that if you do really try to find, or if you do really find significance with a non-parametric test, you can be pretty well assured that that actually is a true difference there, because that p-values are going to be much harder to hit. And so one of the traps that a lot of research will fall into is going under the assumption that they're working with a Gaussian distribution, in which case you're going to use parametric tests without actually doing a test for normalcy, and then they're going to find positive results. You know, they're going to find they're going to be able to reject that null hypothesis, and then they really shouldn't have in the first place, because again, the tests they're using already failed one of the assumptions because they couldn't prove that it was normally distributed data. So in a lot of cases, you're going to find that we'll talk about the specific test later on. We're going to find that the researchers will just kind of fall back and use the non-parametric test, just because, again, if you do find a difference there, you're much more confident that it is a really true result. And so, like, for instance, when I did my coral snake research, this is one of those things where I was like, I have no way to really test for normality with the small data set that I have. It wasn't really going to show any good results there. So what I went ahead and did is just assumed that it was non-parametric data, and I went ahead and subjected it to non-parametric tests. So that way, if I did find a result, I was pretty sure that it was going to be a really true result there. And then if I didn't find anything, then it could have been a type 2 error, but I was at least sure I wasn't going to make any unnecessary type 1 errors. Okay, next we're going to talk a little bit about outliers. So how did the outliers arise? This can happen from a number of different reasons, some of which can include things like if you have invalid data entry, could just be due to biological diversity in some cases. Random chance can do this. experimental mistakes, and just a wrong assumption. So for instance, if you're dealing with a Gaussian distribution versus something different like a log normal, something that just looks way different than what a typical kind of bell-shaped curve looks like. So lots of reasons why outliers will pop up here. And as you remember, if you go back to the second lecture, which one of those mean or median tends to be more sensitive to outliers? And of course, you'll remember that the mean tends to be more sensitive to that, where an outlier can really skew your mean higher or lower, whereas the median tends to be insensitive to that, because again, the median's at 50 percentile value. So looking at the need for outlier tests, you're going to see that by identifying outliers can be very challenging. It cannot be done informally. And so again, we tend to have a tendency to see too many outliers and tend to be a little bit more biased when we're evaluating these. So again, that's why it's very important to do the proper statistical test for this. So again, if you see outlier tests being performed, that's why they're doing it, to make sure to see if the values they're showing there are truly just due to random chance or if it could be an actual outlier. So again, looking at this type of data, you can see that even though some of these values look like they could be outliers, so for instance, if we're looking at something like this data set here, you see these group, and then you see this kind of one little point out here, you might think, hey, that looks like an outlier. Or say, for instance, this value here looks like an outlier. But if you actually do the test, you'll actually find that none of these can be considered to be outliers. So again, our eyes are not very good at kind of scoping these things out, so just kind of fall back and rely on those statistical tests. So questions you want to ask yourself before using an outlier test, was there a mistake in the data entry? Did somebody accidentally sneeze on the keyboard and hit a 0 when they shouldn't have? Is the outlier really, sometimes you can see in the data entry stuff that outliers are actually a code for a missing value. So sometimes, if you're coding different things by different values, it can appear like it's an outlier when really it's just a missing number with some of your data software that's out there. Maybe you notice there's a problem during the experiment that could explain the result there. Perhaps you can have extreme values as a result of biological variability, or is it possible the distribution is not Gaussian, right? And we know how we can deal with that by just running a normalcy test there. So again, these are all kind of questions that researchers will ask themselves to determine if a value is truly an outlier before subjecting it to an outlier test. So these tests, basically, if you answered no to all the previous questions, you kind of have two possibilities. One, that extreme value came from that same distribution as all the other values, and it should not be treated specially. It should be included in the same calculations and tests as all the other values. On the other hand, though, you could find that the extreme value is a result of a mistake, in which case you could either remove it or correct it. But typically, you want to be kind of transparent in those sort of things, unless it's like a really obvious mistake, like you typed something into Excel wrong. But in a lot of the research, they will say like, hey, we have these outliers. This is why we think the outliers are there, usually in the discussion section of the paper. And so basically by doing the outlier test, this can tell us that if the values were really sampled from a Gaussian distribution, what's the chance you would find one value as far away from the others as what you observed? So if you perform the outlier test and found a low p-value, basically what you could say is that the chances of finding a result as extreme as this or more extreme is very, very low. It's more likely, very unlikely to just be due to random chance. And so you can reject that null hypothesis that the data is being sampled from a Gaussian distribution, in which case you may switch over to using something like non-parametric tests, which we'll talk about in a later lecture. On the other hand, if you have a high p-value, that typically means that having a value that high is probably just, high or low, is probably just part of the normal variance there, and so it does not prove that the value came from same distribution as the others, but there's no strong evidence you should reject that null hypothesis, in which case you can still go into the assumption that the data you have is from a Gaussian distribution, so you did the other test for normality. So I mentioned the term robust statistics, and basically this means that instead of eliminating outliers, there are some statistical methods that are designed so the outliers will have very little effect on this, and this is where our parametric tests come from. And again, they tend to be harder to achieve significance. It's harder to hit significant p-values, but the benefit of doing this is that when you truly do have a difference there, you can say, hey, it's very unlikely to be a type 1 error. On the flip side, though, you end up making a higher risk of making a type 2 error, or again, not rejecting the null hypothesis when you should have. And so basically the simplest robust statistic we can look at is the median, because we mentioned the median is very robust because it is not going to be influenced by outliers nearly as much as the mean would, because again, that median is just that middle value, is that 50th percentile. So having a high value or a low value is not really going to skew that very much one way or the other, whereas the mean is absolutely affected by outliers very significantly, and so it would not be considered to be as robust. Okay, so a little bit of Q&A. Does it make sense to ask whether a particular data set is Gaussian? Is it legitimate to remove outliers? What does it mean to remove or eliminate an outlier? And then how should an outlier removal be reported? So first off, does it make sense to ask whether a particular data set is Gaussian? Not really. Basically, you're going to see that it's a common misconception to think that a normality test asks whether the data set is Gaussian. Essentially, what we're seeing is that Gaussian really refers to the entire population, right? So if you had everyone in the U.S. or everyone in the world, they should fall into that Gaussian kind of distribution. Basically, what we're saying is that when we perform the normality test, we're asking whether the data is consistent with that assumption that we are sampling from a Gaussian distribution, right? So if you fail a normality test, it just means the data does not appear to be consistent with those Gaussian distributions. Okay, is it legitimate to remove outliers? Some people see it as cheating, and so a lot of times researchers will go ahead and be transparent about this sort of thing, and try to include reasons why they either included that in their analysis or if they didn't, because in some cases outliers can invalidate your results, and so as long as you maybe do before and after analyses to see, hey, maybe to see what kind of effects the outlier would have, that is one way to kind of get around this, but it's usually in poor taste to go ahead and just remove outliers with impunity. Now, what does it mean to remove or eliminate that outlier? Basically, an outlier gets eliminated. The analyses are then performed as if the value was never collected. So, if the outliers are graphed, they need to be really clearly marked. You can kind of see those when we looked at that censored data back on those Kaplan-Meier survival curves. And then when you're removing an outlier from an analysis, does not mean that the outlier should be erased from the lab notebook. Basically, that value and the reason it was excluded really needs to be recorded and needs to be documented in the kind of the final publication. And how should an outlier removal be reported? Again, oftentimes the papers are going to say, hey, we remove this many values as outliers, and here's the criteria we used to remove them, and here's why, and here's what our reason was behind that. And then it's up to the reader to determine whether this made sense or not, whether it was appropriate. All right, so that's it for this section. If you have any other questions, please let me know, and I'll see you guys soon.